electronic and material physics, magnetic materials play a crucial role in the performance of high-frequency components such as inductors, transformers, antenna, and microwave absorber. With the miniaturization of electronics, particularly in RF and microwave systems, there's a growing need for materials that can maintain the high magnetic permeability while minimizing energy loss. Traditionally, thin film made of nanostructured soft magnetic material have been used to enhance inductance. However, this study explored an alternative approach using metallic ferromagnetic nanoparticles embedded in a nanomagnetic matrix. These composite systems offer the flexibility to tailor magnetic behavior by adjusting the physical properties of the nanoparticles such as their size, shape, orientation, and also distribution. However, designing such composite comes with several challenges. First, high-frequency applications are severely impacted by two types of magnetic loss. First, ferromagnetic resonance (fMR), which is a natural frequency at which magnetic energy is lost due to the oscillation of the magnetic moments. And the second is eddy current loss, which occurs when changing magnetic field induces circulating currents in conductive particles, leading to heat and energy dissipation. To improve performance, we need material that exhibit high permeability, minimal loss, and high fMR frequency. Objective. The main objective is to use phenomenological theoretical framework to model the magnetic properties of nanoparticle composite. The second one is to explore the impact of particle size, shape, and the volume fraction on the effect permeability and resonance behavior of the material. And the last one is to determine the ideal packing configuration of nanoparticle that provides the best performance at GHz range frequencies. Methodology. There's 4 key materials parameters. First one is saturation magnetization (MS), which represents the maximum magnetization the material can achieve. Second one is anisotropy field (HK), the internal field that influences how magnetic moment align within the materials. The third one is damping parameter, a factor that quantifies the loss of magnetic energy due to the oscillation. And the last one is electrical conductivity, which influences how much eddy current loss occurs. These parameters are used within the framework of effective medium theory (EMT), specifically the Boltzmann and Maxwell-Janet models to estimate the overall magnetic response of the composite system. The model is applied to scenarios involving isolated particles and those in contact to simulate different packing densities. Key equations like the Landau-Lifshitz equations and Kitten's formula are used to compute permeability and fMR frequency across different configurations. Particle size. One of the most significant findings relate to the particle size. As particle size increase, eddy current losses also increase. This is because large particles allow more surface area for induced current to flow, which absorb magnetic energy. This study found that particles smaller than 100 nanometers in radius exhibit negligible eddy current losses below 10 GHz. This means that keeping particle size within the nanoscale is essential for applications like RF inductors and sensors. This finding set a practical design constraint. If the particle radius exceeds 100 nanometer, magnetic loss begin to significantly degrade performance at target frequencies. Particle shape. Particle shape also has a critical influence on magnetic behavior. Spherical particles tend to show high low-frequency permeability but lower FMR frequencies. In contrast, rod-shaped particles show the opposite behavior, high FMR but low permeability. This is due to how the shape influences the demagnetization factors along different axes. The study compared sphere, rods, and thin film geometries using shape-dependent analytical expressions. Interestingly, the best balance is achieved with moderately elongated particles, those that lie between sphere and rod with an aspect ratio around 2. These particles provide sufficient permeability while raising the resonant frequency to use levels. Packing arrangement. Now let's talk about how particles are arranged, also known as the composite packing geometry. Two types of configurations are modeled. The first one is bulk packing, the second one is thin film packing. Bulk packing, where particles are distributed randomly in 3D space, and the thin film packing, where particles are aligned in a 2D-like structure with their easy magnetization axis parallel to the film surface. By combining all three factors, small particle size, optimal shape, and thin film-like packing, the range of configuration with outstanding magnetic properties for a volume fraction of 45 to 55%, the modeled composite showed that low frequency permeability values between 3 and 18 and ferromagnetic resonance frequency between 10 and 18 GHz. These values are highly desirable in applications such as integrated circuits where impact and efficient magnetic components are essential. In conclusion, demonstrates the power of theoretical modeling in guiding material design. By carefully tuning the physical structure of magnetic nanoparticles, specifically their size, shape, and packing arrangement, we can engineer composite materials that optimized for high-frequency application. The study emphasized that particles must be smaller than 100 nanometer to avoid eddy currents law. Slightly elongated shape provide the best trade-off between permeability and FMR. And the last one is thin film packing is preferred to enhance directional magnetic properties.